Today's COFFIES Seminar is by Dr. Robert Cameron. He's a scientist from Max Planck Institute for Solar System Research in Germany. He got his PhD from the University of Sydney, Australia, and then has been a postdoc at Caltech and Science University of Tokyo in Japan. In 2003, he joined the Max Planck Institute and has stayed at MPS since then. Dr. Robert Cameron has broad research interests in solar physics in both observations and theories. His studies include sunspot and active region physics, solar convection, and solar dynamos, as well as solar cycle variations and predictions. He is also interested in solar stellar connection, such as star spots and stellar dynamos. And I believe he will be talking to us about the long-term variation of the solar magnetic cycle today.
Yeah, okay. So this talk is with the result of lots of research by Manfred, Jia Jiang, Hannah Schonker, Tom Duval, Emre, and it's on the observational constraints on the sun's global dynamo. And the conclusion for the first part of the talk, at least, will be that the solar cycle involves a net toroidal flux in each hemisphere, and therefore the surface magnetic fields play a crucial role in the solar dynamo. So let me begin with the data, which are the difference between now and 40 years ago is, or 50 years ago, is we have lots of magnetic field observations, full disk, line of sight in particular. And from this, if you look at the center of the disk, you can get the radial field. And if you look towards the limbs, so the east and west limbs, for example, you get the phi component of the field. And this allows you to make magnetic butterfly maps. And on the left, we have magnetic butterfly maps from WSO for the last 49 years. And on the right, we have from Wilson Observatory, which covers 30 years, something like this. And we're all more or less familiar with the radial field maps at the top, but very important as well for understanding the solar dynamo is this azimuthally averaged phi component of the field shown at the bottom. And since these are not so commonly discussed, I thought I would point out that what we measure when we measure the phi component of the field is flux emergence. So the blue map, the blue and the red column map is from WSO magnetograms, the phi component measured by looking at the limbs. The black dots from Karen Harvey. This is where sunspots have emerged. And you can see the usual sunspot diagram. The sunspots overlap where we have lots of toroidal field coming through the surface. And also from Karen Harvey, we have the bands. This is where we have ephemeral regions emerging with a preferred or east-west orientation in accordance with Hale's law. And you can see these extend the butterfly wings back in time to higher latitudes, and they nicely overlap with the blue phi component of the field. And we can understand this particularly well if we consider, so we're looking at the limb, a flux tube, which is rising, the line of sight component of the field will be orientated towards us. So basically the phi component of the field corresponds to the tops of loops as they emerge through the solar atmosphere. I should point out that I'd like people to ask me questions as we go through the talk, because if you get lost, it's an opportunity for me to get you back into the conversation before we lose too much. So B phi corresponds to emergent flux. The equations I'm going to need for this talk are the induction equation. I'm going to apply Stokes' theorem to the induction equation to get the evolution of the flux with some surface in terms of a line integral. So remember, Stokes' theorem is essentially just the fundamental theorem of calculus applied in two dimension. So it converts a surface integral into a line integral. So A is the surface and delta A is the edge of the surface, the contour. I'm going to, when I evaluate this surface integral, it will turn out that the diffusive term, the eta curl B, is very, very small. You can keep it if you like in the analysis, but it is more convenient to drop it at the outset. This is completely different from dropping it in the area. So in the surface area, the induction equation, you have to keep the eta. It's critical for the dynamo action. However, on the surface, when you evaluate this line integral, its role is going to be negligible and can be ignored. I'm also going to follow the traditional notation and introduce the axisymmetric mean by brackets and perturbations with either dashes or lowercase letters or both. So doing this, we get the time integral of the mean field. So the integral of the A of this will be a flux through the surface is equal to, and then we have the expression on the right, which we evaluate at the right integral. I'm going to go back in time for a little bit and discuss work from 2015 and 2020 and look at the net toroidal flux for each hemisphere. And the motivation for looking at the net toroidal flux is actually the observations. So if we look at this, we can see that during maxima, all the flux in the northern hemisphere is basically red, all the flux in the southern hemisphere is blue. This is the toroidal flux emerging for the surface. This at least motivates me to look at the net toroidal flux through each hemisphere. I'm going to concentrate on the northern hemisphere, and Stokes' theorem then tells us that the net toroidal flux through this area, the area inside the dark contour, the bold contour, is equal to, and then we have U cross B plus U cross B, where these are either the mean fields or the mean contribution from the small scale fields. And I'm going to show in the next part of the talk that the amount generated by the differential rotation is about 5 to 8 times 10 to the 23 maxwells per hemisphere. And this is generated by the axisymmetric velocity field and the axisymmetric magnetic fields. And the amount we lose through the surface due to flux emergence is going to be of a similar order of magnitude, about 3.3, 3.55 times 10 to the 23 maxwells per cycle per hemisphere. And so what this will show is that the flux which emerges is accounted for by the toroidal flux being wound up to produce, by differential rotation, to produce toroidal field. So we begin with the toroidal flux generation. We're going to begin, first of all, with the part of the contour in the interior. And in the interior, we place this beneath the tachocline, beneath the convection zone, where no field penetrates, or at least none of the 22-year cyclic component of the magnetic field is going to penetrate. Therefore, the cyclic component will be equal to 0, and there'll be no contribution from the interior part of the contour. We can move into a coordinate system rotating with the equator. We can do this because the equator here is all red, just moving into orange. So there's very little radial differential rotation. In contrast, there's a lot of latitudinal differential rotation, and there's lots of high latitudes radial differential rotation. But if we move into a coordinate system rotating at the rate of the equator, then we have the large scale you feed it and you fire components of the velocity will vanish, and therefore there'll be no contribution to the line integral from the equator. Similarly, at the axis, we also will have the u phi is equal to u theta is equal to 0, but there'll be no contribution from the axis either. And this is good because it means the only contribution to the generation with axisymmetric flows and fields is coming from the surface. So it's something we have to evaluate at the surface. We need to know the velocity at the surface and the magnetic field at the surface. Well, at least we need to know the radial component of the magnetic field, because this is also comes into this integral. And we can measure, and we have measured for the last 40 years, the radial field, and we have measured the differential rotation by heliososmology, by local correlation tracking, by direct Doppler. So we know the terms which go into this integral. It's differential rotation times surface radial magnetic field, and this gives us the integrand, which we then integrate between 1 and 0, so across the northern hemisphere. And this is where we get the generation by the large scale axisymmetric field and flow is 3 to 8 times 10 to 23 Maxwell's per cycle per hemisphere.
Robert,
Yes.
there seems to be a question from Gustavo.
Yeah, can you ask?
Yeah, can you hear me?
Yes.
Yeah, so can you go back one slide, please?
Yeah.
So you are completely neglecting the shearing effect of the tachocline in this case. Is that right?
Yeah, okay. So again, what I'm assuming is that along this axis, this term going from bright red to beneath the tachocline where it's slightly orange, I'm neglecting this term for the moment. I can include it, no problem. I'll come back to this in a little bit later, but the tachocline everywhere else is certainly included.
The strong toroidal field that could be generated at the tachocline is included.
Yeah, sure. So this contour goes underneath the tachocline. So the dashed curve here is the base of the convection zone, and you can put this black curve deep enough so that it's underneath the tachocline. I'm not here saying, discussing in this slide the role of the tachocline. We'll come back to the role of the tachocline in 20 slides, but here it's included. Yep.
Okay.
This is just Stokes' theorem, again, applied to this contour. And this contour is placed so that it includes the tachocline within the area. So the tachocline is within the
Okay, so you're choosing your contour such that you are already in a solid body rotation level.
Yeah.
Okay.
But we'll come back to that in the future. Okay, but what this shows at the moment is that the polar fields are what's generating this 3 to 10 times 10 to 23 Maxwell's per cycle per hemisphere. And as has just been mentioned, I cannot say whether it's radial shear which is doing it. I cannot say from Stokes' theorem whether it's radial shear in the tachocline or it's latitudinal shear. But we'll come back to that later in the talk. At the moment, it's generated, and Stokes' theorem doesn't tell you the generation mechanism, it just tells you how much is generated. So now I want to look at the toroidal flux loss. So we go back to the induction equation to which we have applied Stokes' theorem. And now we're going to concentrate on this little u and little b terms. And we're only, because we're looking at flux emergence, we'll be looking at these little u and little b terms through the photosphere. So I wanted to show you an image of what happens when flux emerges on the sun. So we have here some active regions which have emerged, some more will emerge. And what you see is they tend to spread out after emergence, and they tend to get weaker. So this one up the top is a particularly good example. In 26, it's reasonably compact. Going to rotation 27, it's spread out more. 28, it's really starting to get spread out and weak. And 29, it's almost in the background level again. Okay, conceptually, we can look at the sun from the top and sort of imagine what's happening. We have a flux tube, or we have magnetic flux inside the sun. I'm not assuming it's flux tube. It's just drawn this way for simplicity. Some of it emerges. It spreads out, but it gets weaker. It's getting weaker because we're having submergence of some of the magnetic field. It reconnects, goes back inside the sun. As you go, it spreads out further as time goes on. Some of it goes back inside the sun. But the important thing is, if we're looking at the average toroidal field, then the amount lost in all these cases is the same, because the change in the mean toroidal field depends upon the flux above the surface multiplied by the distance of the legs. So as it spreads out, it gets weaker, but it turns out this quantity d times the distance between the legs and the flux in the loop is a conserved quantity. So it doesn't change in time. And you can sort of see this if you go back to the movie. Yeah, it gets weaker and weaker, but it's spreading out quite a lot. And if you want to do it quantitatively, then it's done in the paper Cameron and Schultz 2020. So again, the idea is we have flux. Initially, we have lots of flux in a short separation. As time passes, lots of this flux retracts back inside the sun, but the amount which hasn't retracted has spread out further and further. And so if you look at the product of these two, it's constant in time. And there's a relatively simple geometric explanation for this, which is basically, so after emergence, the field evolves. The plus and minus fields evolve in statistically the same way. And because the system is linear, as soon as you say they evolve in the same way, you end up with this being a conserved quantity. And this is a good thing, because now we can measure flux emergence as it's happening. We know the average velocity from measurements of using Hinode, for example. You can measure the velocity of these loop tops as emerging through the solar surface. So therefore, we can calculate the amount of toroidal flux which is lost. And this is a simple calculation. Yeah.
Which physical law it kind of leads to that flux times the distance being conserved?
So this comes from, for example, the surface flux transport model, which is based upon observations. So this is an observational result. Yeah. So it turns out the observations say, after your flux has emerged through the surface, the positive and negative, the magnetic field behaves as quarks. And by this, we mean there's no difference between a negative quark and a positive quark. And therefore, as the positive flux spreads out, yeah, I would like to be able to draw. I cannot draw, how unfortunate. And so the positive flux, you begin with the negative flux. As it spreads out, the center of mass will stay the same. They spread out in the same way. And therefore you can pair them. So even though they've actually disappeared beneath the surface, because the system's linear, you don't have to treat them as having disappeared. You can say we have a positive and a negative quark, and the positive ones have spread out, the negative ones have spread out. They spread out in the same way, and therefore the distance between the quarks, between pairs of quarks, is always the same. Yeah, this you may have to read the paper. It's described in this paper.
Thank you.
Okay. Let's hope I can get back to not having a pen. Okay. So now we can measure flux emergence. We know the average field is about 200, is given by the observations. It's on the order of a Gauss. We know the velocity at which it emerges, 200 meters per second. So we can calculate how much is lost. It's just 1 Gauss times 200 meters per second times pi over 2 times the radius of the sun. This pi over 2 radius of the sun, this is just a geometric because we're integrating from 0 to the poles. And when we do this, we find the total amount of flux lost is about 3.8 times 10 to 23 Maxwell's per cycle per hemisphere. You can calculate it in different ways. So Bieber and Rast in 1995 looked out in the solar wind at 1 AU and inferred that a total of 5 times 10 to 23 max was being lost. You can also do it using the very detailed measurements of Harvey et al., Karen Harvey and Hagner in 2003. They measured the properties of ephemeral regions, and you can use those properties to directly determine how much was lost. And you get about 3.3 times 10 to 23 Maxwell's per cycle per hemisphere. So all these numbers are roughly consistent. Multiple ways of measuring it all give about the same answer, which is about the same as we get generated by the differential rotation of the field lines passing through the solar surface. So the field lines passing through the solar surface generate basically a similar amount, a little bit more than we lose with the surface during flux emergence. The next thing I want to say is the more toroidal field we generate, the more emerges. And this comes, and this is basically the way we predict solar cycles. We look at the polar field or proxy for the polar field, which in this case is the minimum 8 index at the end of a solar cycle. And this is a proxy for the polar fields. And we look at a proxy for toroidal flux loss, which is the sunspot number. And they fit in a nice little straight line. This was worked by Wang and Shi in 2009. You can update this to include cycle 24, which is here. And you can also include the predictions of Upton and Hathaway, which I took from their website, or the prediction from the latest prediction in the paper I could find from McIntosh, Lemon, and Egeland. And these are all basically consistent. So if either of these two predictions comes true, it will basically mean we cannot disprove this theory from this cycle, in cycle 25. So far we've seen that the polar fields have a crucial role. It's the flux going through the poles which gets wound up to produce a toroidal field, which produces at least enough to account for what we see. And when we produce more, we see more coming up from the surface. So the question is, where do the polar fields come from? And why do these vary from cycle to cycle? That's a slightly difficult question. So I'm going to ask myself an easier question, which is, how does the polar field change from the cycle minimum, so T1, to the next cycle minimum, T2? And I like this question because it becomes, how does the net radial flux in a hemisphere change from time 1 to time 2? And of course, if I talk about the net radial flux, then I'm back to Stokes' theorem. And now my area is going to be the whole northern hemisphere, the photosphere in the northern hemisphere. And my contour is going to be the equator at the level, at the height of the photosphere. So Stokes' theorem, this is the same equation as before. We're applying it to a new area and to a new contour. And when we do this, the maths is even simpler. We get the change in the toroidal flux. The radial flux for the northern hemisphere is just equal to 2 pi r times contributions coming from radial velocity carrying a theta component of the field across the equator. So this is flux emergence, and a term coming from small scale motions in the north-south direction carrying radial magnetic field. And this will turn out to be dominated by the turbulent diffusivity, because at the equator, the alpha effect and pumping, at least in the kinematic ones, are expected to vanish. So we can see if this actually works. We have two contributions. On the left, you see the contribution coming from flux emergence, so radial motions carrying north-south field across the equator. In the top panel, we see a little red circle with nothing happening. In the middle panel, which is 1 month later, we see something, yes, is beginning to emerge. And by the last panel, we see there's been a significant emergence, and most of the negative flux is in the southern hemisphere, and all of the positive flux is in the northern hemisphere. So this event has carried flux across the equator. The other term is shown on the right. And here, if we look at the radial magnetic field, and we see, very interestingly, that there's a large-scale organization to the field we see in the 1980s, early 80s. We see red field, so negative field in the northern hemisphere, positive field in the southern hemisphere. And this, by turbulent diffusion, causes the transport of negative flux into the southern hemisphere and positive flux into the northern hemisphere. This reverses, of course, from cycle to cycle. And if we just take the observations, we can calculate, we can put in the tilt angles which are observed. And if we do this, what we find, okay, so this systematic part here and this part here, the random component, are both coming from tilt angles. So during the emergence process, there's a slight preference. So we have Hale's law, which gives us the east-west orientation, but we also have Joyce's law, which says, for example, in 1980, that the flux emerging in the northern hemisphere, the positive polarity was slightly closer to the pole than the negative polarity. So the leading spot is slightly closer to the equator, and this transports flux across the equator. And so the tilt angles of active regions are what gives you both of these effects. If we include the actual observed tilt angles, then the flux in the northern hemisphere closely matches what you get from the model, just evaluating this integral essentially. And if you don't include the actual observed tilt angles, but you just include a parameterized form of Joyce's law, then you get a very wrong answer. And so all the noise and all the structure coming in this, in the observations, how much flux you're getting across the equator, is coming from variations of the tilt angle. So this shows us Joyce's law, and the fluctuations in the tilt angles are very important. And we'll come back to that in a moment. But at the moment, let's just recap where we are. We have the net flux is removed at a rate of about 3.3 times 10 to 23 Maxwells per hemisphere per cycle by flux emergence. Slightly more is generated by differential rotation of magnetic field threading through the solar surface. Any field lines which don't thread through the surface don't generate net toroidal flux in either hemisphere. The flux threading through the surface ends up at the poles at the end of the cycle, and the amount which ends up there depends upon how much flux it equated during the cycle. It has a systematic part due to Joyce's law and a component. So this justifies the conclusion that the surface fields play a crucial role in the surface solar's dynamo, so does Joyce's law. It also allows us to discuss budgets. So we can make a budget for the toroidal field. The toroidal field is generated by the large-scale differential rotation, so the axisymmetric flow acting on the axisymmetric field, and it's lost through flux emergence. In the toroidal field, we have flux crossing the equator, And the amount which crosses the equator depends upon the latitude at which it emerges and joystill. And we have the amount which is actually in the northern hemisphere. So we'll end up with two budgets which describe what's happening on the sun. I want to go back to a question which was asked at the beginning, which is the role of differential rotation. And the point I'm going to make now is, well, this is our differential rotation. We have Stokes theorem. We could have chosen a contour which did not cross the tachocline. And if we chose a contour which didn't cross the tachocline, then we would end up with the flux being generated by the latitudinal differential rotation. And the amount which would be generated is proportional to the amount of flux, and it's proportional to the difference in the differential rotation at this surface, so close to the equator, versus close to the pole. So the differential rotation, this structure inside doesn't matter. The only thing which matters for how much net toroidal field is produced is the amount which is produced at the two opposite edges. Okay, and so here you have a lot of toroidal flux being produced because you're going from red to dark purple. So you're scaling this whole range from 300 to 450. If you want to generate the field by the tachocline, then you're going to have a problem because your flux is it may be the same flux, it may be more flux, but the differential rotation is very small. So to get a significant quantity of flux being generated by the tachocline at those latitudes, you're going to need a very large amount of flux. And this amount of flux is going to be much higher than the amount of flux spreading through the poles. And then you have to wonder where's that flux is connecting to, because it cannot be connecting out here. It's got to be connecting locally. What's happening, it must also be generating flux then wherever it's connected through. And why is the amount of flux going through here then related to the amount which is going through the pole? Of course, you can use the radial differential rotation at high latitudes, and here there's no problem. You're going from blue to orange or black to orange, so you're doing this part of the journey at high latitudes, and at low latitudes you're doing the remaining thing from orange to bright red. So what you learn from this is if it's simply the field coming from the pole goes into the tachocline, comes out, I'm not quite sure what picture you have in mind, then most of the flux is going to be generated at high latitudes. So my conclusion here is that in any case, the flux produced.
Robert, sorry.
Yeah. Yep.
So what do you have radial flux? If you have this contour, the only flux that you have there is toroidal.
What?
According to the Stokes chart.
Yeah, so I'm talking about the production of toroidal field.
Yeah, but if you want to apply this theorem, you cannot think about phi r or phi theta. The only phi that you have is phi phi.
Yeah. So phi r tells you what's produced. But if you look at the theorem, you've got this U cross B dl. And U cross B dl is going to be the U is the U phi, and the B will be the BR. So on the left hand side, you're right, you only have the B phi. But on the right hand side, you're going to have a BR.
But you don't need any flux. You don't need any flux. You use the field that is parallel to that contour at any point.
No. So you need the U cross B to be parallel. Yeah. And you need and U is going to be in the U is going to be in the, we'll talk about differential rotation. So it's U phi, and therefore it's going to have to be BR. You need a radial. What gets sheared up by the differential rotation is the radial flux. Yeah, so you need a radial flux which is sheared by the radial differential rotation, and this produces a phi component of the field. And the amount it produces, the amount of flux you get produced, is proportional to the differential rotation times the flux.
Okay, okay. I think for the radial flux you need phi theta then.
And
But okay, you go ahead, go ahead. I will think.
Yeah, so we can go back. So here you're looking at the latitudinal flux, the latitudinal differential rotation. Yeah, and so across here, you have the differential rotation near the equator, and you subtract the differential rotation near the pole, and you multiply it by the flux. And because the pole is rotating fast, because the equator is rotating fast and the pole is rotating slowly, you've got a huge difference in the rotation rates between these two surfaces. And this flux here is the theta component of the flux. So it's flux, it comes in from the surface, it goes along, and then it goes into the other hemisphere. When you do the radial, the contribution from the radial differential rotation, then it's radial differential rotation acting on radial field, which gets sheared up, and the amount you produce in this box just depends upon the radial flux across the box. Okay, so I'll skip that. So I'm not saying in any case that you should ignore the tachocline. I'm just saying if you think the tachocline is generating a toroidal field, then it's mainly going to be generating, or if you think the radial shear is generating a toroidal field, it's mainly going to be generating at high latitudes, very little at low latitudes. So in any case, we have a problem with we need transport for. So
sorry, so what's the assumption on the B?
What?
Do you have some assumption for the magnetic field below the surface when you drew this conclusion?
No, so all I'm saying here is the amount produced, it depends upon the difference in the rotation rate at the bottom, at the two edges of your surface. So it depends upon the rotation rate here and the rotation rate here. Yep, that also goes into this. If you want to know the change in the toroidal flux here, you need to know the difference, which is the difference between the rotation rate at the top and the bottom of this box times the amount of radial flux going through the bottom and therefore going through the top.
Okay, I see.
Yep. But that's all I'm saying. And I'm saying you've got a lot of radial shear here and very little radial shear here. So if you think your field lines are doing this, then you're going to be producing all your toroidal field at high latitudes, and you'll need to transport it. If you come up with some other mechanism, so for example, if you thought this was how it was working, then you'd have shear, and you think this field is huge because you need a lot of flux here to make up for the low shear, then you've got a lot of other fields which you really need to be thinking about what they're doing. And I think it's going to be somewhat problematic, but I'm not stopping people from doing it. What I'm saying is obvious way, even if you go on the tachocline and think it's something like this, you're going to have to transport your field. If you think it's latitudinal differential rotation, you're going to have to transport the field. And this is basically where the flux transport part of the Babcock-Leighton flux transport dynamo comes in. It comes in because we generate the toroidal field at 55 degrees or above. We can generate it either with radial or latitudinal differential shear, but it's going to happen at high latitudes. And we need the flux emergence and we observe it to occur close to the equator. It needs to occur close to the equator to get flux across the equator, which is critical for producing the colloidal field of the next cycle. Similarly, the colloidal field of the next cycle comes from flux which is across the equator, and it somehow has to be transported to the poles. And fortunately, the transport to the poles at the surface we can see. This is without question really on circulation of the surface. What's happening inside the sun? Not so easy. We can't directly see it. It's consistent with at least my preferred helioseismically inferred meridional circulation. But if you tell me it's something else, if you tell me it's transport by turbulent pumping, sure, fine. This one we can observe. This one, I'm not sure. But in any case, we need some transport mechanism. We're going to need, if we want to make a dynamo model, we also need to know something about flux emergence and where Joyce law comes from. And the easiest thing for flux emergence is so the subsurface toroidal field is related to what emerges through the surface. What's more tricky is Joyce law. And Joyce law is tricky because it's a small effect. So if you look, for example, here, which is this is average emergence, and this is by Schunke and Schunke in 2019. You can see pre-emergence, there's very little there. Time of emergence is more or less east-west aligned. Afterwards, slightly, maybe you would say, it's a small effect. And the question, of course, is, are we talking about those associated with a buoyant flux tube? So this would be all the work on thin flux tubes. Are we talking about convective flows? This would be all the mean field work. Or are we talking about some other flows which are not purely convective, but are magnetically driven, so some other type of alpha effect? And the answer turns out to be hard to tell. So we've got very nice, and I'm not going to go into detail, but very nice work done in the 90s and early 2000s, where people showed that flux tubes emerging from the base of the convection zone, if they had the correct range of field strengths, reproduce both the observed tilt angle, the latitudes of emergence, and the asymmetry in the field strengths between and structure between the leading and traveling polarities. However, let's go and look at Joyce law again. So Joyce law basically states that there's a relationship between the phi and the theta components. So you have an emergence. The emergence takes both a phi component of the field and a theta component of the field out of this sort of the surface. The picture before was something like this, where we measure the tilt angle, and the tilt angle, let's be simple, is about a quarter of the latitude. Okay, so from this, you can deduce that the average theta component of the field due to Joyce law is equal to the average value of the toroidal field, all of which is coming from flux emergence, times 10 gamma, where gamma is tilt angle and gamma is equal to 0.26 lambda. This is all happening near the equator, so therefore we can get that the theta associated with Joyce law is just some simple mod 0.26 times the latitude times the value of the phi, where this is now all in radians. So this is quite nice. And we also have, so outside of flux emergence, the B theta associated with Joyce law will be 0. This is by definition, we only get Joyce law B theta during the emergence. Before we saw the emergence velocity is about 200 meters per second from Centeno. So now we can have the mean value of UR B5. So the U is going to be 200 meters per second. The B theta is equal to 0.26 times this V is the same. This is just this times B5 times the latitude. This is just substituting this equation. This is substituting equation 1 into, and just basically multiplying by VEM, which is a constant. Why do we care? Well, this UR B theta appears here. So if you just take the induction equation and we just looking at the R component of the azimuthally averaged R component, which is what we observe, and it's the radial magnetic field butterfly map, then it has a contribution coming from flux emergence. So this is the contribution here coming from flux emergence. This other term is a diffusive term. This is coming from the random water supergranulation, and this one's coming from the meridional flow. But this term is coming from flux emergence. And what we see here is we have a way of evaluating it. So if we put it in, then we get the change in PR associated with Joyce law is equal to, well, it's just this term. It's just this term. It's just this term. And we can now substitute in that this is equal to this. And we end up with the change in the radial magnetic field at the solar surface due to Joyce law is equal to 0.26 times the emergence velocity, 200 meters per second, divided by geometric factors. And then critically, this is a B phi. Yeah, so we've converted B beta here into a B phi using Joyce law. And for those of you who know mean field theory, this appears quite attractive because this is what we get from Joyce law. So this is pure geometry, Joyce law. And what we get from the alpha effect, well, the alpha effect tells us that the change in B with respect to time is equal to the curl of alpha B. So the change in BR, we can look at the radial component, is equal to 1 on, so some geometric factor times B phi. We can estimate alpha at the surface, for example, due to supergranulations. We get the radial component of vorticity is this, we have correlation length. And so we can calculate alpha due to, for example, the turbulent supergranulation motions. And we get this formula here. We can evaluate this numerically, and we find that the change in the radial field produced by a turbulent alpha effect has this form. And this is very similar to what we require for Joyce law. So this is essentially telling you that quantitatively, a turbulent alpha effect will produce something like Joyce law. The turbulent alpha effect operating at the solar surface can account for Joyce law. So what we end up with is, yep, these two terms are similar. The alpha effect can account for Joyce law. So, yep, it could be a Joyce law coming from turbulent alpha effect. It could be Joyce law comes from the Coriolis force acting on the rising flux tubes. It could be some other type of alpha effect. And the reason why we cannot tell the difference between these, or why it's at least difficult, is because the emergence velocities are similar to the convective velocities in the top 20 megameters. This is research from Birch et al. 2016. So all these velocities will be acted on by the Coriolis force, and all of them are of the same order of magnitude, and therefore it's very difficult to say whether it's a Coriolis force acting on the flows of the tube or whether it's a turbulent alpha effect. Regardless of where Joyce law is coming from, we can just put it into the model, and when we do this, we then have a complete dynamo model, and the eigenfunctions of the model, it's a linear model, and the linear model eigenfunctions at least resemble the observations. I'm not going to discuss it, but they also, the same model, if you put in the observed noise level, reproduces the statistical properties of the solar cycle over the last 10,000 years, obtained from cosmogenic isotope, cosmogenic nucleotides, or from the actual observations of sunspot models. And the reason it does this is actually very generic, but for details, I'm going to have to refer you to this paper. So the new part to add here is Joy's law is important. There's several possible causes, and it's difficult to tell the difference between them. I want to just, before I finish, mention the nonlinearity of the dynamo because it's quite pretty. This is at least one nonlinearity which I think is important. And it goes back to the Waldmeyer effect. The Waldmeyer effect is that strong cycles rise quickly and then decay, whereas weak cycles rise slowly and then decay. And this is from Waldmeyer in 1935, 1941. And this isn't particularly pretty, but this one I think is pretty. This is the same plot from Waldmeyer's 1955 book. And now he has two different things. First of all, the latitude at which the butterfly wings emerge is the same for all cycles. They emerge at 28 degrees, they propagate towards the equator, and at the end of the cycle, they're at about 6 degrees. Strong cycles, weak cycles, they all go in the same way. In the initial phases, strong cycles rise quickly, weak cycles rise more slowly. And this is what you would expect from different amplitude cycles. What you do not expect, and what's really quite pretty, is that in the decay phase, declining phase, all the cycles fall into a universal behavior. So there's a universal behavior, and where a cycle falls onto that universal behavior just depends on how strong the cycle is. And this I find, this implies some really nice nonlinearity in the dynamo process. You could ask if this is just, a sketch which Waldmeyer, whether it survives the modern data. The propagation towards the equator is the same for all cycles. This certainly survives. This is halfway, 2011. Here's a new version of the Waldmeyer effect, done from all the cycles we have up to now, the cycles 11 to 24. And you can see strong cycles, weak cycles, all propagate towards the equator in the same way. They have different amplitudes in initial phases and different, but all the same behavior in the decline phase. And this is true for the activity level. It's also true for the width of the butterfly diagrams. So different here, strong cycles, medium cycles, weak cycles behave in different ways, but at the late phase of the cycle, all behave in the same way. And this is basically the result of Cameron and Schultz of 2016. All cycles declined in the same way. And Jiang in 2020 points out that this is possibly an important nonlinearity. And there's a Biswas and Bidia and paper by me 2022, which provides a potential explanation. And I want to stop there, but I will take questions. Hello?
Well, if you'd been unmuted, you would have heard a lot of cheers here.
We were clapping here.
Okay. Do people have
Right.
questions?
I'm not seeing any raised hands yet. Okay, how about I ask it? I have a question. In the mean field dynamo model that you showed in the end, I know you didn't talk about it in detail, but how is buoyancy handled? Do you like cut toroidal flux from the interior and assume it escapes?
So this particular two-layer model is in this, it's in the Babcock-Radian sense, it's a two-layer model. So what we have is, I consider the evolution of the all the toroidal field, the integrated toroidal field from the base of the convection zone or beneath the tachocline to the solar surface. And I only consider this. Then it's a two-layer model. I have the radial field at the surface in the model and this integrated quantity. If you want to move into 2D, then you have to, so if you want to move into, for example, if you want to include the radial dependence, then you just have a whole lot more parameters you have to consider. So one thing you need, and you can tell you need from observations, is some pumping. And you need the pumping because if you don't have pumping, the polar fields just decay way too quickly. And they decay because your field just leaks out to the surface. And what you want is the field to leak out with a decay time of about 11 years. So I mentioned that flux emergence carries flux across the equator. If you want to associate a timescale with it, which you can because we know how much is being generated by we know the generation of the net toward the field. So we know how much is there and we know how fast it's escaping. You get a timescale of about 11 to 20 years, which is interesting. And if you don't have no pumping, then and you have a diffusivity of 100 kilometers squared per second, then it escapes too fast at least. And this is why there was at one point a debate about advection / diffusion dominated regimes. And I don't have anything useful to say on this. But what I do want to mention is this timescale. This timescale is compatible with a field stored, for example, toward a field at the base of the convection zone, just diffusing outwards with a value of the turbulent diffusivity on the order of 100 kilometers squared per second. So I'm not sure if you need buoyant flux tubes or whether you can get away with a turbulent diffusion of the field. What we know is a lot of the field is, most of the field is lost through the upper surface. Whether that loss is due to buoyancy, or whether it's due to just turbulent carrying of the field, hard to tell. And it's hard to tell again, partly because the velocities have to be on the order of the convective velocities, otherwise to be consistent with the observations, and this is Alan Birch's result. So whether or not it's buoyancy, the convective velocities is still important. And therefore turbulent diffusion will still be important. And this comes back to the question of whether what's also producing Joy's law, which flows are really critical, and I cannot answer that question with this analysis.
Thank you, Robert.
Yeah.
Right.
Hi, Robert. I have a question on, it's a very general question. How will these calculations be affected by fossil fuel in the radiated interior? I mean, if there is
So this is mainly concerned with the 22-year component of the field. If you have a fossil field which is slowly leaking out, this would be superposed on top of this analysis. So it would presumably enter as a 22-year periodicity. So you would still do the same analysis, and you would just, when you began very near the beginning, when you're evaluating this contribution from the bottom, you would have a non-22-year component which would be continually leaking out, or which would leak out in a way which was periodic but not with the 22-year. So
will that leave a signature on the surface?
Yeah, but so presumably it would leave a signature with a periodicity of 22 years, not 11 years. And so I know people are interested in possible variations on 22-year periods rather than 11 years. but that's outside the scope of this talk.
All right. Okay, thank you.
Vidya has a question.
Yeah, Robert, very nice talk, very interesting result. At some point you were showing that using the Joyce law, you can get the same amount of radial field from the toroidal field. And also you can use the mean field theory where you can estimate, where you can make a rough estimate of alpha effect and you get the same amount of radial field. So now so then you can't actually distinguish between the Babcock-Layton type source
No, so
and the
for me,
alpha.
no, so for me, this is all Babcock-Layton. So the original Babcock-Layton papers do not discuss flux tubes emerging buoyantly from the base of the convection zone.
Okay, I understand. Yeah.
Yep.
Okay. Mhm.
So and the question of whether it's a flux tube emerging or whether it's a more traditional alpha effect happening at the surface, this is difficult. So if you go back far enough in time, I don't think people expected there to be any toroidal field at the solar surface. But there is. It's small, it's on the order of a Gauss. But one Gauss field turns out to be enough to be consistent with the observations and produce Joyce law. And the basic issue again is that the velocities we're talking about are convective at the same magnitude as the convective velocities. And this makes distinguishing between them very, very difficult. The timescales are also, the timescale of granulation of supergranules is 1.6 days. Timescale for flux emergence, and therefore Joyce law is on the order of a day or two. The timescales are the same, the velocities are the same, the Coriolis force comes from the rotation of the sun, it's the same. Difficult to tell the difference, but they're all within the Babcock-Layton framework.
Yeah. Okay.
All right. The next question is from Nick Brummel.
Hi.
Hey, Rob. Sorry. Thanks for thought-provoking talk as always. Yeah, I'm interested in this idea of all the things you were just talking about in terms of the timescales all seem to be roughly the same, and so therefore, I've been thinking about it in terms of the sigma effect, but the rise time is probably the similar as the convective overturning time, blah blah blah. So it's kind of hard to just extract everything here. The thing that struck me about one of the things you said is that, and you can confirm, or maybe some of the other flux emergence people here can confirm. You only sort of see Joyce laws after things have emerged through the surface. So it's the sort of time-dependent effect where it starts with none and then acquires it. So it hasn't acquired its tilt.
That's the observation. It goes back to Kosovachev. I think he's here, maybe, and Stenflo. It's also found by Hennes Schunke. I did not comment on this talk.
But is that what happens?
That's the observation, yeah, and I believe the observation to be true. But what it means, and it's true in an average sense. So if you average over a large number of active regions, they begin on average with no chill, and then they develop a chill. I believe that to be true. Its interpretation, I don't know.
Yeah, I think that's super interesting though, right? Because I mean, all of these interpretations, whichever sort of alpha effect you want to pick, the large scale Babcock-Layton or the Parker, a smaller scale. I mean, you would think that it would have tilted it earlier, right? Why does it emerge non-tilted and then only gets tilted after it's emerged?
Yeah, but so if I had to guess here, and I'm reluctant to do so,
you're amongst friends.
Yeah, but beneath the surface, we've got a very strong turbulent dynamo, small scale dynamo going on. And so I'm not actually sure I understand the distinction between Rife and the alpha effect and the sigma effect as soon as we're beneath the surface, because in the presence of the small scale dynamo magnetic field, this distinction between basically of the scales of the magnetic field becomes blurred. I just don't know how to make a distinction. So helicity I can understand, but a distinction between Rife and twist in the presence of a very strong small scale dynamo, this I don't have a feel for.
Yeah, well, that's exactly what I've had a student working on that sort of stuff. And yeah, it's interesting that if you immerse a flux tube in a very, strongly kinetic helicity thing, I mean, the sigma effect says that it transfers kinetic helicity into Rive and therefore into the opposite twist, right? But in reality, we don't find that at all.
Yeah, and the question for me is what is this small scale dynamo-magnetic field doing? Because basically the difference between Rive and twist is a difference of scale. And as soon as you say there's a small scale dynamo, then I don't see how you can maintain this distinction between the different scales. But it's a super interesting question, and I'm looking forward to reading you and your students' work. Yeah.
Sounds good.
So that's sort of what I'm thinking at the moment, but yeah, I'm reluctant to comment because I don't have those calculations that the student are doing.
Oh, we haven't published them yet either, but he's got his thesis defense on Friday.
Okay, nice. More questions?
Gustavo?
Hi, Robert. Thank you so
Hi.
much. Very, very nice talk. It's me again.
Yeah.
So I'd like you to explain again, because it's not clear to me, where is the certainty that is a Babcock-Layton happening here?
So certainty is too strong. I mean, the nature of physics is we're always one observation away from, our best theory being complete junk. But the idea is that the surface is playing a key role. For me, this is what a Babcock-Layton dynamo means. And the evidence that the surface plays a close role is that the amount we generate for the surface is the amount we lose. So you can go back to papers from the 80s, and they were always talking about, 5 times 10 to 23 Maxwells as being the flux required to produce the activity. And this is basically correct. We need about 5 to 8 times 10 to 23 Maxwells to produce, to account for what we see. And this is produced, and this has to be produced by flux threading the surface. There's no way you can have flux threading the surface, which doesn't end up producing so much per hemisphere. That's just Stokes theorem. But the other thing which makes it look like it's a Babcock-Layton dynamo is this one. So the more you generate, the more emerges. And this is basically how people are now making predictions. And this, of course, is far from, being definitive evidence, but you can see there's a reasonable correlation here. And this is basically the amount which is being produced and the amount which is emerging for the surface. So what we have in favor of the Babcock-Layton model are, first of all, okay, let me go back. We see it here. In one hemisphere at maximum, you've got one polarity flux. Yeah, so it's this, okay. And then you look at how much is produced, and it's equivalent to how much is lost, and if you produce more, you lose more. This makes me think that the net toroidal field is an important quantity. And as soon as you say the net toroidal field is an important quantity, then the surface fields become important.
That's right. But until here, I agree with you. But
for me, for me, that's a Babcock-Layton bit.
So this is not exactly the canonical Babcock-Layton mechanism where you get the spreading of the decaying active regions going towards the poles. That's what So in mean-field models, that is how the Babcock-Layton mechanism is included.
Okay, and And then, okay, so I can go on, sorry. So Joyce law is then critical. There's no way for it not to be. And basically it comes from, it comes from this integral. So as soon as you say the polar fields are important, then you say, how do we get the polar fields? And the polar fields, it turns out, so if you look at this type, you've got no field, no field, no field, and then all the flux is concentrated in the polar fields. So again, it's a conservation argument. The only way you can change the flux from here to here is to bring stuff across the equator. Yeah. And the way you get it across the equator is either you emerge across the equator, and you can look at the statistics of the emergences across the equator and there's no preference. And the other way is you take some of this blue stuff and you carry it across the equator because it's slightly closer to the equator. And then you've transported flux across the equator. So this integral is basically what tells you that Joyce law is critical. And that what's critical is getting flux across the equator. And then you say, where does Joyce law come from? And at this point, you're out. The Babcock-Leighton mechanism doesn't distinguish. So it could be, you know, the thin flux you picture, or it could be the mean field approach. I can't tell the difference. But you need Joyce law. Joyce law is essential because you have to get the flux across the equator.
Right. You need the cancellation.
Yeah, you need the cancellation. So cancellation is coming from Joyce law, and if you do the model, you find it actually works very well. So actually, this is better than I would have imagined.
There's another question, if I can.
Yeah.
Because in 3D global dynamo models, you get a cycling behavior with a magnetic field close to the poles, with not so close to the solar butterfly diagram, but it works.
Yeah.
And there is not such a thing like Joyce law in this kind of models, so it still works.
Yes. So no. So here I'm actually, you know,
So
I've tried to pay attention to the field.
your argument is
I'm
that
not
you
quite
need,
sure. So
you need Joyce law.
Yeah, so Joyce law is a subtle thing. It's even on the sun, it's a small difference between it's a small tilt angle, and so it's difficult to measure. So yes. So if you end up with net, so if you have field radial flux at your surface, which at least in a number of dynamo models I've seen they do, then you have some type of flux emergence. The flux emergence is presumably entirely diffusive, but this is okay because even on the sun, I cannot tell you. So flux emergence is not the same as turbulent diffusion. Yeah, it's possible even on the sun. So flux emergence is just turbulent diffusion. So the two are just different names for the same physical effect. And of course, turbulent diffusion will have a phi component of the field just below the surface, and this will be acted on by your turbulence, which will have an alpha effect, and you will presumably be in this regime where you have a Joyce law, which is related to your alpha effect. You won't typically produce or necessarily produce a dynamo which is as dipolar as the sun. So on the sun, it's very, very clearly massively dipolar. I've seen simulations which have many features which reminiscent of the sun, cyclic, etc., but they're not as clearly dipolar as the sun. So, but that's probably not critical. So if you look at the radial maps of the sun, for example, and the ones movies I showed before were better, but at minimum, the field is all at the poles. Yeah, very dipolar structure. Many simulations don't have this structure, but whether or not they're Babcock-Laden, for me, is unclear. Because so the dipolar Babcock-Laden needs to get flux across the equator, but I could have a quadrupolar Babcock-Laden where it wouldn't be flux across the equator, which would be important. It would be flux separation between the poles and near the equator in each hemisphere. So, so for me, the important thing is something like Joyce law, but again, this could be a turbulent alpha effect. And the critical thing is and what I think really makes the Babcock-Laden work is that what's important is the net toroidal field in each hemisphere. Yeah, I think as soon as you say it's a net toroidal field in the hemisphere, which is how this dynamo is working, then you're somehow talking about a Babcock-Laden type dynamo where something like Joyce law must be occurring so that you get separation of the radial flux at the surface, which can then be acted on by the differential rotation. But we can discuss that.
Yeah, no, thank you. It's very interesting. So it should be very nice to make this analysis on the results of these simulations to see what.
Yeah, so I think there's work being done on this by Sasha Brun and his group.
Yeah, okay.
Adam Finley, yeah.
Thanks again. Very nice talk. Thank you.
Okay.
Great. Thank you, Robert, for the very interesting talk and indulging all of the questions in such detail.
Okay.
And
Thanks everyone for listening.
Also, thank you, Robert, for staying up late. This must be past your normal work hours, right?
Yeah. It's almost 9:30. Thank you to the organizer. We see you.